Okay, we're on.
Welcome students to the College Prep Chemistry Chapter 7 test hints. Mrs. Gregory here.
Mr. Sustin here.
And here we go. So hopefully some of you have figured out that watching these hints at the beginning of the chapter actually gives you a great preview and some background as to what we're doing throughout the whole chapter.
Right.
Have any of your students done that?
There are a few dedicated, motivated students who
Have figured that out?
they were early on the bandwagon of printing out the test hints
Yeah.
at the beginning of the chapter to use as a checklist while we're going along.
Gotcha.
Right.
Okay, so hopefully you're watching these videos not the night before the test. Although that would be good, but maybe a couple times before that too.
Better late than never.
All right, let's go. Number one. We have 30 questions on this test, and 24 of them are multiple choice. 6 of them are short answer. Of course, you know that because you printed the test hints.
Right.
Identify the number of valence electrons in an atom. So we're going to ask you about a particular atom. You'll have your periodic table. By now, you've looked at that so many times that and written configurations, you know where to find these elements on the periodic table. But what if we said, how many valence electrons are in phosphorus?
Is that one F? Is phosphorus F?
Phosphorus, no.
Oh, that's P.
Phosphorus is P, because that's where they found it.
There you go.
Phosphorus is element number 15 on the periodic table. It is in column 15. And if you know that.
Or 5A, depending which periodic table you happen to be looking at.
We're looking at how many valence electrons, so that's the S and P electrons for phosphorus. It's got 2 S electrons, and it's the third element over in the P block for a total of 5 valence electrons. If we asked you about rubidium, it's in column 1, 1 valence electron. If we asked you about aluminum, it's in column 13 or 3A. It's got 3. Okay?
But what if we were despicable and ask them about zinc?
Zinc.
Which is in the valley. It's in the D block, the transition metals.
Yes.
But
it's at the end of the transition metal. So it's got that d orbital filled. So I would go with the S electrons there. Now, in this chapter, you have seen that sometimes those d electrons are included in the valence shell. And your handy-dandy periodic table gives you a clue with the oxidation number as to what that would be. But I would say that zinc would be a +2 charge because of the 4s2, the 2 s electrons in the 4s sublevel ahead of time. Moving on.
Number 2, define valence electrons.
All the easy ones.
Yeah, look that up. It's in the book. Look it up.
You guys are awesome with this. You already knew this when we started talking about it back in chapter 2.
Yeah.
Okay?
This was one key thing we were all very happy that you guys remembered from 9th grade and 10th grade when the biology teachers went over it a second time.
All right. Number 3, apply the octet rule in the formation of an ion. Well, octet means 8, and the octet rule tells us that elements want to have 8 electrons in their valence shell. Of course, you know what the valence shell is. And some of those atoms do that by losing valence electrons, the metals will, and some elements, the nonmetals, will do that by gaining valence electrons. Whatever it takes to get it to 8. Let's grab the placemat here. Your placemat right here. It's got periodic table.
Is that going to be big enough?
I don't know. We'll find out.
Here.
So, look at how far away the element is from the closest noble gas. If it's on the metal side of the chart, it's going to lose valence electrons to get there. And if it's on the non-metal side, it's going to gain valence electrons. I'm stalling a little bit because Mr. Sustin's grabbing a periodic table for us. And here we go. We have,
Here we go.
so a metal over here, column 1, 2, something in column 3 is going to lose those valence electrons, so the D block. And elements over here in the non-metal side are going to gain valence electrons. Just count how many boxes over to get to the noble gas.
This is another instance where this is elementary school math.
Right.
And you cannot let the chemistry get in the way of these math skills that you're already good at.
Right.
Number 4, write the electron configuration of an ion. You have to know how to write the electron configuration of an atom.
Right.
and then remove one electron, or add an electron, or 2 or 3. I advise my students to use the orbital diagram, the arrow diagram, perhaps, rather than the electron configuration.
Right. So if we ask you about a specific element and we say that element's ion, like the sodium ion, okay? We know that the configuration of a sodium atom is 1s2, 2s2, 2p6, 3s1. We know that sodium is a metal. We know that metals want to lose valence electrons to become ions. And, Mr. Sustin, what's it going to lose?
Sodium is going to lose that valence electron. Here's the first energy level, second energy level, third energy level. Third energy level is the outermost, the highest energy level, and it has 1 electron in it. That's the one it's going to lose.
So how would we write the configuration of the sodium ion? How would that look different than what you've got here?
Oh,
Show us.
I would do this.
Awesome.
And voila, it's gone. And then I would also add myself a note that this is now an ion. This is the sodium ion.
With a +1 charge.
With a +1 charge.
Okay. And if it was a nonmetal, we'd just be adding to that P block for whatever element, say oxygen or chlorine or something like that, to fill it up to end in P6. So oxygen, here we go.
Just because that's an easy one to change.
Yep.
So there's oxygen, 1s2, 2s2, 2p4. It's right here in group 16 or 6a, depending on what your eye goes to on the periodic table. It has 6 valence electrons in the second energy level. It's looking to gain 2
Because that will
electrons.
give it 8, the octet.
So this would be 2p6, and it gained 2 electrons. It has that -2 charge, and
That's configuration.
that's it.
So I noticed that when you wrote this, it ended in P6, and when you wrote the sodium one, the sodium ion, it ended in P6. Do all ions end in P6?
Most of them do. Most of them do. There are some small elements that are
Some
exceptions.
exceptions.
But sodium wants to get to the electron configuration of the nearest noble gas, which is neon, which ends in P6.
Right.
Oxygen wants to have the electron configuration of the nearest noble gas, which again is neon, which ends in P6.
P6. Cool. Number 5. The hint says, identify the charge of common anions. Now you need to know that, or remember that the anions are the negative ions. And ions, or atoms become negative ions because they have gained electrons. So, and the electrons are negative, so they're becoming more negative. So we're going to be up here in this non-metal corner of the periodic table for elements that commonly form anions. And if we want to know the charge on, say, the fluoride ion, fluorine is 1 away from the noble gases, so it is going to have a charge of -1, gained 1 electron. Oxygen, like we saw here, is going to have a charge of -2, it's 2 away. Nitrogen, -3, it's 3 away. So take a look at where the element is in the P block, how far it needs to go to get to that noble gas configuration, how many electrons it would need to gain. If it gained 4 electrons, it's going to have a charge of -4.
Yes.
Moving on, number 6.
Number 6, define the octet rule. Why do I keep getting these?
I don't know.
Look it up. It's in the book.
Oh, the definitions.
Yes, define the octet rule. You need to know that elements are looking to arrive at a full valence energy level, which usually contains 8 electrons.
Right.
Some atoms lose, some atoms gain.
We defined this already, didn't we?
Probably
in
3
our
times.
first hint.
Yeah, probably 3 times. Look it up. Use that book.
Alrighty, number 7. The hint says, count the number of electrons needed to be gained or lost to form a specific ion. So this question will ask you about an element and it will say, tin. How many valence electrons would tin need to gain or lose to become an ion? And this one is kind of a tricky example because tin can
Yeah.
actually do a couple things. Tin could lose these two to have an ion of +2 charge, or it could lose these two and these two to have an ion of +4 charge. But we probably would ask you something easier. What would be another one that
Well,
maybe gain or lose to?
going back to the previous question you just did, take a look at these guys up here
Right.
and just count how far away are you from the nearest noble gas. If you're closer to a noble gas, 3, 2, 1 electrons away, then you're probably going to be an electron gainer, and you would gain 3, 2, or 1 electrons. If you're way over here, then you're an electron loser. Metals are electron losers. Your valence energy level is mostly empty, and you're going to be looking to,
Right.
dump those couple electrons.
Those of you who had Mr. Tobel in 9th grade probably remember left side losers, right side receivers. That's how he couched it to his class. So
Cool.
maybe that's stirring something up in your brain.
Number 8, identify the common ion produced by a specific element. This question sounds almost like a repeat.
Right.
Hammering home this point because we're going to need it in upcoming chapters.
Right.
How many electrons are you going to gain or lose? And how does that translate into a charge?
Okay, so here's how they might be looking at it a little differently. Oxygen wants to gain 2 valence electrons to end up in P6. Oxygen could gain just 1 and have a -1 charge, but that's not the common ion. In fact, it's rare. So yeah, we could have an atom gain 1 or 2, but maybe it really wants 3. So we want to look at the most likely ion.
Right, same on this side. Beryllium could, I suppose, lose 1 electron. But that really doesn't do anything for it in terms of satisfying the octet rule, which you just looked up.
Right. And our hint for number 9 says similar to number 7, so you're seeing a little bit of repetition here. We have several questions that are very similar. We're just asking you about ions in various spots on the periodic table, and if you know how far it needs to go to get to the octet, you're in good shape.